This lesson is for Advanced Algebra, Lesson 5.8 on graphing systems of inequalities. Over the last few lessons, we've been graphing a lot, and now we're going to be graphing more than one inequality at a time. There's some vocabulary I'd like to have students read and copy before we get into the first example. Solution to a system of inequalities is the intersection of half planes. Not the planes that fly through the air, but a two-dimensional surface like what you see on a coordinate plane. So when multiple planes intersect, that's going to be the solution that we're looking for. Those points in the intersection are called the feasible region or the feasible set. The corners of those feasible regions are called the vertices. Individually, each one is called a vertex. You will find the vertices by graphing and sometimes solving. So those will make more sense once we actually try it with an example. So here I've got a system of inequalities. Notice that there's 4 of them, so we're going to have to graph 4 things. And it asks us to graph and give the coordinates of the vertices of the feasible region. Then it asks us if these particular coordinates are within that region. So we're going to go ahead and graph, and then we're going to figure out what the feasible region looks like, and then identify the vertices. Right away I have x greater than or equal to 0. I know that that's going to be the vertical line right along the y-axis and everything to the right of that. Then I have y is greater than or equal to 0, which is the horizontal line right on top of the x-axis and everything above that. So what these two pieces of information are telling me basically is that I'm working in quadrant 1 only. A lot of word problems that involve real life situations will have that type of thing going on in the inequality or the system itself. So know that when you see that, you don't really need to shade all of quadrant 1, just know that that's the only place where you're working. I'm going to go ahead and number the other two equations. The first equation I'm going to label as a number 1. It's in linear combination form, so I'm going to fill in a 0 for x and a 0 for y to get the x and y intercepts. If x is 0, then I know that I have to solve 2y equals 12. 2 times 6 is 12, so I know that my point there is a 6. If I start all over again now and plug in a 0 for y, if y is 0, I'm going to simply have x plus 0 equals 12, so x has to be 12. If I graph those coordinates now, I get 0, 6 is up here at 6, 12, 0 is out here at 12. I know I'm going to be connecting with a solid line, and then I want to figure out where I'm going to shade. If I plug in 0 for x and 0 for y at the same time, that would indicate the point 0, 0, and I'll try to figure out if that coordinate makes a true or false statement. If I plug in a 0 for x and a 0 for y, I'm going to get 0 is less than or equal to 12, which is true. So I know I'm going to be shading below the line. I'm not going to waste my time right now and actually shade this in because remember, we're going to be shading multiple things. So I'm just going to remember right now my feasible region is this triangle right in here, because remember we're to the right and we're above. So right now all of those are overlapping just in this triangle. Let's graph equation number 2 by again making a little table. If I plug in 0 for x, y has to be 12. If I plug in 0 for y, x has to be 6. It's a coincidence here that we ended up with the same numbers as before. That won't always be the case. So now I'm going to graph 0, 12, which is up here, and 6, 0, which is over here. I'm going to connect those with a solid line as well. Then when I decide where to shade, I plug in 0 and 0 for both again. So I'm going to get 0 is less than or equal to 12 again. So again, I'm shading below. So you can see now that the feasible region for where I'm shading everything and where it's all overlapping is just this region here. So there are other places that would be shaded, but this is the only location where I would have shaded all 4 equations in an overlapping fashion. So that's the feasible region here. That's where everything would have been shaded all together. Now I need to identify the vertices of that feasible region. Clearly I've got a corner here at 0, 6, got a corner down here at 6, 0, corner down here at 0, 0, and then I've got a spot here where the two lines cross. Looks like they're crossing at 4, 4. Let's verify that. If If I plug in a 4 for x and a 4 for y, I'm going to get 8 plus 4 is 12. That's true. And that'll happen in the second equation as well. So they cross indeed at 4, 4. Know that you could use algebra here to ensure that that is where they cross. If you graph accurately, however, you probably won't need to do that. So those are the vertices of my feasible region. When we move on to lesson 5-9, students will know then what to do with those vertices and will apply a real-life application to them. For now, students just need to practice finding them. I'm going to have students work on two more equations, two more systems, which are from their homework. So let's look at question number 9. Graph and find the vertices of this feasible region for y is less than or equal to 2x plus 3 and y is greater than negative 3x minus 4. So students can do this problem. They will need a full x and y axis on graph paper. Keep in mind that these are both in slope-intercept form, so you won't need to do the table on this one. You can do a table. Tables will always work for you when you're asked to graph, but in this setup you don't need a table to graph. You can simply start with the y-intercept and then do the slope, rise over run. Remember, if your slope doesn't have a bottom number, stick a 1 under there. So students, go ahead and graph both of those on your own and pause the video, and then the answer will be revealed. So I went ahead and numbered these again. I did the first equation in blue. So it had a y-intercept at 3, and then I went up 2 over 3, up 2 over 1, up 2 over 1. I did a solid line, and then to decide where to shade, I plugged in 0 and 0. 0 is less than or equal to 2 times 0 plus 3. That's true. I end up with 0 is less than or equal to 3 there. That's a true statement. So I wanted to shade on the side of the line where 0, 0 is. 0, 0 is on this side of the line, so I shaded that area below the blue line in turquoise. Then I went ahead and graphed equation number 2 with a green line. The green line starts at negative 4, and then the slope is negative 3 over 1. So from there I go down 3 over 1. I could also go up 3 and left 1. I'm going to do a dotted line there for that one. And then to decide where to shade, again I fill in 0 and 0. If I plug in 0 for y and 0 for x, I end up with this statement: 0 is greater than negative 4, which is true. So I shade on the side of the green line where 0, 0 is, which is also to the right. So you can see that I shaded everything to the right of the green line in green. So the area where I shaded both is kind of a triangular shape, starting here, traveling to here, and then going down and everything to the right of that. So my feasible region is doing this. One side of the feasible region is dotted, one side is solid, and then it's everything in between. So you can see there that I've double shaded in that section. This only has one vertex. The two lines cross in one location, so I only need to find where that one location is. On this situation, it's not real clear where they cross, so I'm going to go ahead and use my skills from earlier in the chapter where I learned how to solve systems to try to figure out what the answer is for x here. Since both of these are equal to y, I set them equal to each other. Remember, when you're trying to find where the two lines cross, you're imagining that these are indeed equal signs. So if I know that they're trying to find where they are equal, I'm going to set them equal to each other. I'd add 3x to both sides to make the 5x, subtract 3 from both sides to make the negative 7, divide by 5 on both sides, and I get x equals negative 1.4. If you plug that back into your equation, you'll be able to solve for y of 0.2. So that's where those two lines cross each other. They cross at negative 1.4 and 0.2. So that's question number 9. I'd also like students to do number 10. This one has a little bit of a tricky element to it, and I want to make sure students are able to follow that very well. So again, give yourself a large graph space. Again, you'll only need quadrant 1 for this one. You will go back to using tables now on the first two equations because those two equations are in linear combination form. Quick heads up here on the bottom two, just a quick sketch for you so you can kind of see visually what's going to be happening here. You're going to be using the x and the y axes, mostly in quadrant 1. You know you're going to be doing everything to the right of the y-axis. That's what this one is telling you. And then you also are going to have a horizontal line at 7. So when you draw your line at 7, we want everything below that. So right now, when you're graphing, you're really only working with this region of the graph. I don't know that it's important for students to really shade that region right now. Just know that when you're graphing, you're going to have that horizontal line and you're going to be doing everything below that. So again, it might be kind of nice to just draw the line and then draw a little arrow for yourself, reminding you that, hey, where they overlap is just going to be below that line and everything to the right of that line. So students, go ahead and graph this on a nice big graph, and then graph the remaining 2 diagonal lines with using tables. And students, the answer will appear here on the video. I would recommend pausing now so that you can try it yourself and then you can look at the answer. So I'm going to make this a little bit smaller so it's a little bit easier to see. So I went ahead and I graphed. There's my y equals 7, and I would shade below. I numbered the top equation as number 1, and I did that in dark blue. When I plugged in a 0 for x and a 0 for y separately, I got 0, 8, and 16, 0. So this is 0, 8 here, 16, 0 is out here. And let's go ahead and label that just to make it a little bit easier. And then I connected those with a straight line and I shaded below. Then I graphed the second equation down in light blue. Again, I made a table for that. 0, 18 was way up here and 0, 6 was down here. Connected those with a dotted line and shaded to the left of the line. So then it's hopefully easy to see that there's a feasible region right in here. So this little corner right in here does not get included in our feasible region. The feasible region goes from 0, 0 up to 0, 7. Over here, which we'll talk about why it's 2, 7 here in just a second. On your graph, it might actually show up as 2, 7. There's a point here, and that's where the first 2 equations cross, the dotted and the solid. Again, your grid or your graph, if you graphed accurately with a straight edge, might show that that's crossing at 4, 6. And then we've got another one down here at 6, 0. This is double shaded, or excuse me, single shaded, and this is single shaded. So the feasible region is only right in here, in this little 5-cornered region. So let's just double check here with students on how to find these 2 points here. Clearly that point is on the 7 line, so we know the y value is going to be 7. And then it crosses the first equation that I graphed. So I'm going to plug in 7 for y right here. 2 times 7 is 14, so x has to be 2. So I was able to get that coordinate verified very quickly. I thought it was 2, 7 on my grid from where the grid lines cross, but I was able to verify it in that top equation pretty easily. So I know that coordinate is indeed at 2, 7. Similarly, for this other coordinate here at 4, 6, I know it's where the first 2 equations cross each other. So I did a quick little linear combination just to ensure that it was indeed crossing at 4, 6. So I did a little linear combination with the top 2 equations, multiplied the bottom equation by a -2 to get the y's to cancel. Know that you could have multiplied the top equation by a -3 to get the x's to cancel. So the bottom equation changed to this new equation here. And then I added the top equation to the new equation to get this, and I solved that to get the x of 4. Then I plugged it back in to the first equation and was able to get the y value of 6. So students will need to be comfortable working through this type of process to graph. You need to be able to graph inequalities and find where the double shading or the triple or the quadruple shading will take place. That quadruple shading is called the feasible region. And the corners of that feasible region students need to be able to find either by graphing or by solving or both.